Okay. So we're going to go ahead and we'll do that traverse, and we're going to run through the process, and we'll get our angle, directions, latitude departures, our air enclosures. Traverse precision, ultimately we'll adjust it. I'm going to show you two, well, really I'm going to show you one scheme to adjust, and then with these coordinates. Okay, so you guys have a picture, this little guy. So what you're looking at, that thing represents the traverse. It's A, B, C, D, E. Okay. And we ran angles in there and we ran distances. Okay. So the first thing we're going to do, those are raw numbers. Those are raw angles. Those are raw distances. Now, what we usually do when we're out there in the field, we don't just measure something once. Okay. So you're going to shoot that from two directions and average the distance. Angles are turned in sets. So normally you do 2 or 3 sets. When I was out there working, we usually use we turned our angles and they didn't agree within 3 seconds. We turned them until we got a 3-second agreement. Okay. So those represent redundant measurements. Redundant angle, redundant distance. Everybody with me? Now, this is a really lousy traverse. It's that way on purpose. One thing so that you can see it's bad, so that when you do an adjustment, you're actually adjusting something. The reality is you don't want to adjust much at all. Okay. But unless you float things out 4 or 5 decimal places, you won't see anything happening. Okay. So we're going to round up to 2 decimal places essentially, but you're going to have an adjustment. Okay, this would not be a real traverse. In other words, I would throw this out. Okay, but just to understand, it's because of what we're going to run here. So you're going to go to the second page here, and there's a little angle adjustment sheet. Okay? So what we want to do is start with angle A, and we're going to write that stuff down in there. So I might just minimize. I think that's just going to be in your way, guys, if you're trying to watch that. Is that better? Probably. So we have the measured angle, position. We have what's called a correction. And then we have the adjusted angle. Now, it truly doesn't matter what angle you start with, but I usually start with the one I started with in the field. And the last angle I end up with is what we call the closing angle. Okay, so we're going to take and write those down. We have 64 degrees, 53 minutes, 30 seconds. If you guys find a mistake, let me know. Sometimes when I get going, I will tend to do that occasionally. And we have 107, 33, and ultimately 96, 38. Okay. So those are our field angles. So right below that, you'll see the sum of the interior angles. So what we want to do is come through here and put that in that sum box. Okay, so let's take a minute to do that. Again, if this is where, if you have a calculator that will do this for you very nicely, it really helps. Luckily mine will, if I key it in right. Otherwise, you end up having to convert things to decimal degrees. And back, and that's not always your best bet. So hopefully you can figure out how to do that. You guys tell me what you get when you're ready. I'll write it down. This is my summation column. I got 540 degrees. Anybody have it yet? 2 minutes. And 30 seconds. And I agree with that number. So if you're not getting that number, that's on your end, okay? So we should all have that. Of course, that could be a mistake right there, okay? So make sure you know how you're doing that, all right? So right below that, it says n minus 2 times 180. And we said that that's what we call the what? That's your theoretical sum. That's what it should agree to. So that's the number of angles, 1, 2, 3, 4, 5, or the number of sides. It should be the same. So 5 minus 2 times 180 should give us what? What's that give us? 540. 540. If it isn't 540, we are really out in left field, right? Okay. But it's 540, but it's what? 0 minutes and 0 seconds. So when we subtract the one from the other, we wind up with 0 degrees, 30, or 2 degrees rather, 30 seconds. I'm sorry, 2 minutes and 30 seconds. All right. If we had degrees, we'd have a real problem. Okay. So this is what you call your misclosure. This is referred to as your misclosure. Now, at this point, this would be the place, the first place, you would be looking to figure it out, okay, do I accept it, do I reject it, what? You guys recall what I said you probably would be looking at by today's standards?
In 9 seconds?
Well, I said about 3 seconds per angle would be good. So really, we'd be looking for a total loss of about 15 seconds, maybe, maybe if you allowed 5 seconds total per angle, that's a lot still. This is horrible, okay? So already we have a problem, okay? Now, as you look at those numbers, why do you think this might be a problem? Can anybody see why that could be an issue? What are you noticing about your seconds? This instrument's only measuring to the nearest 15 seconds, probably, maybe even 30, okay? It's an interpolated. This is not the way most modern instruments are reading. They're gonna read to the nearest second, okay? So basically, the least count on this instrument might be 15 seconds. So if we look at that, that may not be that bad of a bust, okay, when we're looking at that. But this is probably was done with a transit, okay? Not a theodolite, not a higher level instrument, okay? So it would probably have been acceptable back in the day, but it isn't acceptable by today's standards. But we're gonna go ahead and adjust it, okay? Now, here's the thing to think about. What is this misclosure telling us? It is what? We are plus 2 minutes and 30 seconds. So what does that tell us about our correction? To get this to 540 degrees, what do we have to do?
Subtract it from right.
Yeah, so our correction is actually the opposite direction of what that misclosure is. So pay attention to that, because you could easily double your misclosure if you weren't careful. If we distributed that and added it to each angle somehow, we busted it twice, okay? So in other words, in our correction column, we're going to have a negative correction for each one of these, essentially. Okay. So now let's talk about corrections a little bit. When you correct them or adjust them, you could look at different ways of adjusting. There's different schemes out there. One is to just kind of, probably the easiest way is to just distribute that equally. So I would take the 2 minutes and 30 seconds and divide it by the number of angles and then just distribute it proportionally, or across the board. That's the easiest way. But what is that assuming when I do that? What is that assuming? Is that every angle was as good as every other angle, or no angle was better than any other? Is that true, or would that be true? Some of you guys that have done measurements out in the field, can you tell me? Is that always true? You're saying no. Why do you think that, Doug?
Not possible.
It's not possible, but things things out in the field cause things to be better in one respect and not in the other. Can you think about anything that can do that? Anybody? Okay, you could have been at a level setup, but you'd have to know you were at a level. That's the thing. I wouldn't turn an angle if I knew I was at a level. But I can tell you point blank, I have set up an instrument at certain locations and you level it and you level it and you level it, it just keeps drifting because of what's happening at that setup. And sometimes you just say, oh, hell with it, I'm going to go with it. Okay. That could have happened. So that means if that was happening at that angle, I might want to put more adjustment in that angle than I do in the other one. So what we're doing is saying now, instead of doing it just across the board, we're looking at what created something and we're weighting that. Okay. Another thing you might weight it against is if I'm sitting here and I got a back sight there and a long foresight like this. This is one of the worst things you can do with an angle. Have a short back sight to a long foresight. Okay. Because if you are out just a little bit on your sighting, you're out a whole lot in your foresight sighting. Your angle changes drastically. Okay. So if you have a short back sight to a long foresight, that's not a good thing. Now we try to not do that when we're out in the field. We're setting up our control. I'm not going to put a 50-foot back sight and shoot to a 2,000 foot. Okay. I'm not going to do that, but sometimes you're forced into it. There might be that reason. Here's another thing, refraction. Refraction can be really bad. On a day like today, in particular, it's really cold out there, right? But if you look over a concrete, or let's say an asphalt parking lot, you're shooting across a parking lot. What's happening to that parking lot on a sunny day? When it's really cold, it's getting hot, and it's getting a lot hotter than the ambient air. And what it'll do is it'll start to produce heat waves across that parking lot. And you can get an issue of refraction differences. I've had it in the summertime so bad, you would set up your target in the distance and you'd be sitting there, and you'd look in your scope and that target's doing this. Seriously, it's dancing. And technically we would just pack up and do something else and then come back to that because you can't do that. In fact, when the high-level NGS guys were doing measurements, they never did their measurements in the daytime because the refraction was a lot higher. If they did it at night, the refraction was a lot lower. Okay. So you got weighted schemes, weighting it. This gets a little bit of air, this gets a little bit more, this gets no correction. Okay. Or we can just distribute it equally. Okay. So by today's standards, probably if you're doing, pretty equal back sights and using the instruments and that kind of stuff, it kind of makes sense for most of us to probably just do an equal distribution. So that's what we're going to do. It's the easiest. So if we do that, how many seconds does that turn out to be that we need to distribute to each? And by the way, we only work to the nearest second. So if you come up with a number like 30.5 seconds, we're probably going to round it to 31 seconds, and then we're going to throw the error in one of those angles. Okay. But this comes out even, does it not? How many seconds do we have?
18.
I don't think so. I think it's 30 seconds per angle, isn't it? You're taking 2 minutes. 2 minutes would be what? 2 times 60 plus 30. Divide that by 5. And that would tell you how many seconds. So we're saying 30 seconds, right? So we're going to distribute 30 seconds across the board. But remember, it's important that if we added that, we were doubling that error. Okay. And that's easy to do. But the one beauty of this is we're going to see that when we do that, we'll be able to take a check. Okay. So I'm going to trim off 30 seconds from this. My adjusted angle is going to be this. Okay, and this gets us what, 206. We get 34.45, is that right? Mm-hmm. We get 64, 20.45. And then we get 107, 33, 15, 96. 8, 15. And that's good, right? Those are my angles. Pretty great there. So how do we know that we didn't make a mistake? There's going to be a lot of checks and balances in this process, so you want to take them every step you can. What's the easiest thing I can do to make sure I didn't make a mistake? Add them up. And if it doesn't equal to that, you blew it. If you come up with five minutes of buzz, you blew it. Okay, you have it. Okay. Or you could just come up with, you just blew one of these numbers. So let's just sum that up and let's see what we come up with. Somebody do that for me, or all of you do it. We all need to know how to do this. What are we getting? You guys that don't have calculators, I suggest that you bring calculators from now on. Very important. Okay. Are we good? Good. Okay. So I would tend to write that under here. You don't want to get into this process and realize that you blew your angles, okay, after you've done it again. So this checks. Okay, so our next step, now that we have adjusted angles, we're going to calculate directions. So usually in this process, you have a starting value that you use. It could be a real number coming from 2 points out in the field, or you just made something up arbitrarily. A lot of times it doesn't matter, because when I get this figure done, I can rotate it into whatever coordinate or whatever bearing system I want it in. Okay, but I have given you a starting bearing, and the starting bearing is from D to E, and that is 81, 42, 15 southeast. So what we're going to do is calculate the bearing from E to A, and then we're going to work it all the way around. Now, one suggestion I will give you, if you're going to look at this diagram, correct these angles on here. What I would do is probably throw a line through the angle and then just correct it with the values here. Because if you use the unadjusted angles, you're going to have your bearings are going to be busted. Okay, your bearing should close flat because this closes flat. Okay, so let's go ahead and I'm going to start drawing pictures up here so that we can kind of look at this stuff. So I'm going to assume that I'm starting at point E. This is E. I'm going to throw my meridian through E. And when I look at that, if I'm sitting at E, I'm backsighting B. So I'm backsighting B in this direction. And we know that the bearing angle on E to D is what? It's southeast, so therefore it's northwest. That's why I drew it in the northwest quadrant, right? And that's southeast 81, 42, 15. 81, 42, 15. Okay. Everybody okay with that? And if we look at E to A, it looks like E to A is in the northeast quadrant. Does everybody agree with that? Right? So what we should see there is we turned the angle at E, which is this. The raw field angle was 96, 38, 45, but we're not going to use that. We're going to use what? Is it that one? Yeah. 38. Okay. So we want to write that down. Make sure we're using this one. Okay. 96, 38, 15. So this will be the bearing from E to A. I'm going to write this stuff over here, but we're going to transfer that into our chart, but just to keep this straight. So that looks like that's going to be northeast. That's what I'm saying. What do we come up with here? Now, this is where we should be able to do this pretty rapidly. Okay? If you can't do that quickly, what does that picture tell me I'm going to do? What's that picture say to do to get that bearing? You're what? Subtracting the red one from the blue one? And what's left there is the bearing that I'm after. You see that? subtracting that from that, I came up with 1456.00. Pretty much agreement. I'll write this down and see if you guys might be wrong. Anybody get that number? Good? Yep, no, maybe? Okay, cool, all right. So that's A to E. All right, so now we're gonna sit up at A at backside E. So now I'm sitting at A. My meridian is now coming through A. E to A was northeast, so therefore A to E is now southwest. The angle there would be what? Off of the meridian would be what? What's this angle right here? 1456, right? 1456. If we look at that picture, and if it's a pretty decent picture, doesn't it look like A to B is also sitting in the southwest quadrant? Doesn't that look like that's true? And we measured an angle at A from E to B, and that was 64.5330 initially. So that is this guy, 64. Did I have a mistake here? Are we good? Is this wrong? It should be 53. Okay, that's right. So one of you guys told me that when you summed that up. We need to check that. So this should be 64.53, right? So how do we get this bearing right here? So we got 1456 plus 64.53. 79.4900 southwest. Agreeing with me? So this is A to B. South 79.4900 west. So this would have been a real problem here, okay? Of course, if you guys would have taken the numbers I had here and you would have summed that, that would have been 1 second or 1 minute off. We got to make sure we're good, all right? All right, so now what do? We pick up, we're sitting at B now, we're going to backside A. Next one is put that diagram over here. I'm now sitting at B. My meridian is coming through B. I am backsiding A. Southeast or southwest rather goes to what bearing? What does it flip to? Northeast. So as I look at this, I'm looking northeast to A. And that means this angle off of the meridian is my 79.41. As I look at my picture, it looks like, oh, wait a minute. I'm good. I want to do this. Put my B over here. So I'm looking towards C, and C looks like it is northwest. Does everybody agree with that? Looks like it's northwest. So we measured a rather large angle here from A to C. And that angle was 206.34.45. Is that right? Yep. I didn't make a mistake on that one, did I? All right, good. 206.34.45. So the bearing angle is actually going to be the angle off of north here, that guy. So in that diagram, what does that tell us we need to do? Yeah, exactly. And that picture tells me everything, doesn't it? Yeah. So that's why those pictures are really so important. Just can't emphasize that enough. Let's take a minute to do that. You guys are verified with me. I got 73, 36, 15. Everybody read that? 73, 36, 15. This would be the line B to C, and that would be a north. 73, 36, 15 west. Okay. Now we got to watch this too, because it's really easy to blow a quadrant. I mean, I could have the south right, but if it's not west, that's going to make a mistake too. You're going to see that real quick when you get into the math. Okay, because there's a bus there. We good? All right, let's come back over here. Now we're going to set up at C, back site B, foresight D. So I'm going to set up my point at C. Draw my meridian through C. I'm backsighting B. B to C was northwest, so therefore it's now southeast. Like that. This angle here, 73, 36, 15. If I look at my picture, it looks like the line C to D is in also the southeast quadrant. So that looks like it would put it here. And we measured an angle between B and D, and we corrected it. So that should be the 64, 20, 45 angle. 64, 20, 45. Okay. So when you look at this picture, this is the angle we're after right there. Okay. So what do we do to get that one? Subtract the one from the other, right? So we're going to take the 73, 36, 15 and subtract from that 64, 20, 45. 9, 15, 30, is that what you guys came up with? 9 degrees, 15 minutes, 30 seconds. This is C to D. South, 9. Let's say 15:30. 9 degrees, 15 minutes, 30 seconds east. All right. Is that looking good? So we're done, right? We've got bearings on every line. Because we know that the line from D to E is what? That was what we initially started with, right? South. 81, 42, 15. Are we finished? You're saying no? Why?
Should we check it somehow?
Yes, we better check it because we're assuming that we what? Didn't make a mistake. And if we made the mistake right here, every one of these is wrong. Okay. Now, the bearings should come back to what we started with because we know that our angles are flat. Okay. So we only use 4 of the angles. So we haven't used the closing angle. So yeah, what we want to do is recalculate that line and make sure we come up with 81, 42, 15. If we don't, we got a mistake. Okay, and we're going to rectify it. So what I'm going to say is I'm going to be sitting at D, backsighting C, foresighting E, and we're going to see if that doesn't agree. Okay, so I'm sitting at D, meridian through D, backsighting C, okay, And that angle that we just calculated, C to D, was 9:15:30. So this angle here is 9 degrees, 15 minutes and 30 seconds. Okay. So D to E is somewhere in the southeast quadrant like this. And we turn an angle of what there? At D, 107, 33:15 corrected. I remember we adjusted that. 107, 33:15. So the angle that we want here to check, we want this angle right here. That's the angle we're at. And we know it should be 81:42. So how would we approach that? Looking at that picture. What's that tell us to do here?
I don't know.
I don't think so. I would subtract this off of that. And then subtract that remainder from it. That's how I see it.
Well, that's what I was saying, I don't know if it's subtract from 180, so that's the same thing.
I guess it does do the same. Let's see. I don't think it will though. Shouldn't. You add them up, you're not, and subtract from 180, you're gonna get the same answer. Go ahead, you do that. And I'm gonna do mine. I'm gonna take 107, 33:15.
I'm gonna be a lot slower.
But that's okay. And I'm gonna subtract that from, that 9 degrees, 15:30. When I do that, I'm telling you that this angle is 98 degrees. There's no way if you add them and subtract from 180, it can work. So I'm gonna now subtract that from 180. I get 81:42:15. You see what I'm saying? If you add them and then subtract from 180, it's gonna give you way less than 81.
Okay.
So here's what I'm looking, just look at this logically. What I'm saying is if I know this green and I subtract that green out, this is what the remainder is 98 degrees. And then this is what I'm at. You see what I'm saying?
Yeah, yeah.
Okay. I wanted to give you enough rope to hang yourself. Okay. All right. Does that make sense? Okay, good. This checked, all right? Okay. So now we have good bearings. So we really haven't even gotten into the traverse closure at this point, but we've got it all set up now because we needed good angles, good bearings, and good distances. So now we're going to go to that next chart. And this is called the traverse closure computation sheet. And so you notice you have a line column, a bearing column, a distance, a latitude and a departure, adjusted lats, adjusted departures. And then you have what's called DMD and double area. That's if you're calculating area stuff. DMD stands for double meridian distance. And we're not going to do any of that. So we're just really going to do the basically 80% of that chart. I'm going to go ahead and set that up on the board here. And we can start filling in some of this and then we'll start calculating things. Okay. Okay, so I have the line. And I have the bearing. Now I want you to understand you can also use azimuths. Okay, so it doesn't have to be bearing. So really just think that can be direction of either type. And the beauty is that if you use the azimuths, as you see later, you don't have to do as much mathematically. Your calculator does a little bit more for you. Okay, but I'm going to do it with bearings the first time, and we're going to give you a homework problem, and you're going to run this through using it. Maybe azimuths might be helpful. Okay, so then we're going to have our distance column, and then we have latitude and departure, and then we're going to have adjusted latitudes. We're going to have we're going to have another latitude and a departure here. And this is what we would call the adjusted latitude and adjusted departure. Okay. So I'm gonna start out and I'm gonna start at point A. So I'm gonna go from A to B, and then B to C, C to D, B to E, and E back to A. Now, really, truly doesn't matter where you start, but you would get slightly different numbers the way they would adjust depending on where you start. So you kind of think about that, but it really, in general, it's going to get the same result. Now, here's the other thing. Make sure that we get the right bearing with the right line. Okay. So we're going to take this guy and write him over here. We have south 794900 west. If you guys find me doing a mistake, please call that to my attention, okay? Because it's real easy to do. Real easy to transpose, and it's real easy to get one of your numbers in the wrong area, okay? So in other words, if I called that northwest, I already blew it. So just make sure that I get it right. C to D, south 9 degrees, 1530 east, south 81 4215, and then ultimately we're coming back okay, that's what we're looking at. So the next thing we want to do then is write the distances. Now, again, remember, we're going to assume those distances were done redundantly. So those represent average distances. Is everybody okay with what I got here? Anybody see any mistakes? We're going to find them if they're right there. Okay. All right, so A to B, this is another place. Make sure you get the right distance with the right line and don't transpose anything. Okay, those are all easy things to do. A to B, 690.88 and 616.05, 677.97, 971.26, and 783.32. By the way, notice those lines are very nice, long lines. So in general, we don't have any short right sides staying on four sides. So that's a good thing. Okay, you guys agree with that? Anybody see any transpositions or anything? All right, so if we sum this column up, this is called your perimeter of your traverse. And we're going to use that number. So let's just go ahead and sum it up right now and put her down here because we're going to need him later on. So in other words, that's how far we traversed. Okay. 690.88 plus 616.05. You guys verify me. Thirty-seven, 39, 48 feet. That's about what? So that's about 7/10 of a mile. Okay, so we're pretty far. That's a pretty good sized traverse. Okay. So remember, your unit here is feet. And these are angles. So our latitudes are also going to be distances, as will our departures. So their unit will also be feet. Okay. So that's something also to remember. How would that change if we were using meters? Would anything be any different if you were using metric measurements? Anybody know? Does it change anything? It won't. Okay. It would just be that your lines would be metrically measured in meters as opposed to feet. You'd still probably be using degrees, minutes, seconds. Although some people, they do use grads. That could be. All right. So our next step, this is a big step here. We're going to take and break our traverse down into what we call latitudes and departures. So a latitude, by definition, I told you this the other day. Let's go through this real quick. Is the orthographic projection of your course, your line into the north-south direction. So what this says is that if this is the east-west direction of your survey, and this is the north-south, so this is your east-west line, and this is your true northwest, north-south line. If I measure a vector like this, where I have measured its distance and its angle, because bearings and azimuths are always measured off of north. If I project that into the north-south line, what that means is you literally would take this down and drop that from a perpendicular down. You come up with that vector. This vector is defined as latitude. And this projection this way is defined as departure. So departure is always east-west, latitude is always north-south. Okay. And the other day there were two equations I showed you on your handout, and it said this: if the latitude of any course is equal to the distance of that course times the cosine of theta, and the departure will be equal to the distance times the sine of theta, where theta can be expressed either as a bearing angle or an azimuth angle. Either one works just as nicely. The only difference is that when you use bearing, because the angle is always between 0 and 90 degrees, your answer will always be positive, but that's impossible because sometimes we're traveling north and sometimes we're traveling south. Okay. And same thing with departure. East is going to be positive, west is going to be negative. So you're going to have to do the sign yourself. The calculator is always going to spit back positive, because the cosine and the sine in that first quadrant between 0 and 90, they're always going to be the positive. Okay, so this is how we handle it. It's really simple. We consider anything north positive, anything south negative from a latitude standpoint, and east is positive, west is negative. So here's what I do. Just keep it simple. Before I calculate a thing, I can go right through here and I can say negative, positive, negative, negative, positive. I'm just going to write that right here. Negative, positive, negative, negative, positive. I know a lot of you guys don't like to put a positive sign there when you don't have to, but I suggest you do. And the reason is because it's going to force you to think. You know, should I be having a positive or a negative here? Okay. And departure, I'm going to look at the same way. Negative, negative, positive, positive, positive. Do that right now before we do anything. And we don't have to worry about it. We already took care of it. Because our calculator will not take care of it. If we do this in azimuths, it will. Okay, so that's the beauty of it. All right, so we're going to start. We're going to start here, do the left, the depth, and we'll just do these. Okay. Okay. So let's take a minute. I'm going to go ahead and calculate these. So you guys, if you disagree or agree, let me know. I got 122.15. Now we're gonna round these to the nearest 2 decimal places, but for the reality, you could float them out further. And here's one thing: if you do this in a computer, which most people do, it floats them out at whatever range it works at. So what it's starting to do is force your precision. We didn't really measure it that high with precision, so it kind of makes sense to to keep it in that room. You guys okay with what I got there, everyone? Did you not get that number? Okay, let's do the departure. We're gonna take 79, 49. Find that. On your distance. Looks like what, 680.00? What I came up with. Anybody agree with that? I'm rounding it, remember the two decimal places. Blank scares. Anybody not?
It's taking me a while.
Okay, all right.
I don't know how to put the seconds in the calculator, so I really can't. I got YouTube. Where I get home.
You have a TI?
Yeah, I got the 18 plus.
Okay, does anybody know how to do it on a TI? Because I can show you how to do it on a Casio. I think you have to do it 3 times, right? TIs are a pain. They're not that simple. They used to be. Well, mine, I have a key that I have to hit, like, so I key in 79 and I hit this key and it says it's a degree, and then I type in 49 and hit that degree key. And so I still have to do that, but I can do it pretty quickly. The TI, sometimes you have to get into a higher level menu. Just write it down, and what you do need to figure out how to do this though.
Well,
Okay.
you just really.
Oh, you got it now?
No.
Okay,
Perfect.
perfect.
You're less slow.
That's okay. That's okay. Perfect. Then. You guys okay now? I'm not great with different calculators, so. All right, so why is this bigger than this? What's causing that? Well, look at this angle. It's what, 79 degrees? That's pretty close to 90, isn't it? If we drew a picture, what's going on there? We drew a picture, 79 degrees is what? Like right here, isn't it? So we noticed that that piece right there is going to be a lot smaller than that piece right there, right? So doesn't it look like the departure should be a lot greater than the latitude? And isn't that what those numbers are telling me, right? Would they ever be the same? Would the latitude ever equal the departure? When? 45 degrees. Because that's going to be halfway, right? Exactly. So here's what I'm trying to get you to think about. Think about that when you calculate it. I can look at this and I can tell you my latitude is going to be a lot smaller. So if my angle is between 0 and 45, I'm going to have a greater latitude than a departure. And if it's greater than 45 up to 90, I'm going to have a greater departure than I do latitude. So just think about it, because you know what? It's real easy to do this. It's real easy to flip them, real easy to flip them. Okay? So just think about it. Think about it. Okay? So let's go and do the rest of these as we get them, and we'll write them down and see if everybody agrees. Okay? 73 degrees, 36 minutes, 15. Cosine. I will write down what I have, and you guys disagree, let me know. Okay? I got 173.89. I'm 91.00. Okay. Anybody? I'm just going to go ahead and crank these, and then if you guys find a mistake, let me know, or you disagree with me. Oh, that was right. Definitely. $69. 16. Notice at 9 degrees, you're almost pure latitude, so you're going to expect a real small amount of departure here. That's what we should be seeing. (908). Looking good so far? One more to do. E6, check these. All right, that's what I'm coming up with. You guys are, anybody agreeing, disagreeing? How we doing? Now remember, you noticed on your calculator, every one of those answers was positive, right? But remember, that's impossible. Now, that is only because of the 0 to 90 reference that we're dealing with in that quadrant. So if we were using azimuths, they're going to come up with that negative or positive sign because they're going to go from 0 to 360, and the cosine of the sine will recognize that. So that is one of the really nice things about that. Does anybody see any mistakes that I have? Does anybody? We're all good. Okay. So what does this do for us? Well, first off, what we're doing is breaking this thing down. Another way of thinking about this, like I said, in statics, they talk about breaking it down into components. That's what we're doing. We're taking the vectors and breaking them down. So the other thing, and I drew this on the board the other day, so I just want to reiterate that because this is a really beautiful way of looking at this. If you have a traverse really simply shaped like that, and we're going, let's say, from 1 to 3 to 4, we're breaking that vector down there, latitude, departure, departure and latitude, departure and latitude, latitude, departure. The vectors going up have to equal the vectors going down. In other words, because these guys would both be positives, these guys would both be negatives. When you add them together, theoretically, they should be 0. So we would say that for a perfect closure, the summation of your latitudes have to equal 0. Okay, if it's perfect. If there's nothing out of whack, you're going to get 0. And departure is going to work the same way. These guys will be positive. These guys will be negative. The summation of the departures theoretically should be exactly 0. But they're not. It can't be for measurement. Okay, so we got that. So what we're going to determine is how much we don't agree with 0. Okay. In other words, we're going to be either greater than 0 or less than 0 is what's going to happen. And that's going to be what we're gonna define as our air and latitude. Okay, so what we're really gonna do is take our latitudes, we're gonna sum them, and we're gonna say that the air and latitudes is gonna be equal to the summation of the latitudes. So we'd like them to be zero, but they can't. And the air and departures is gonna be equal to the summation of the departures. Right. So what we're saying here, you're gonna take this column right here, you're gonna sum it up algebraically. You're gonna take that column and you're gonna sum it up algebraically. And you need to determine not only what its magnitude is, but also its sign, because that's telling you something. Okay. So let's go ahead and we'll do this. Just gonna sum those up. Make sure you get the negative or the positive in there. I came up with a negative 0.6. So this is my air and latitudes. Are you getting that number? Okay. Do the other one. Came up with a positive 1.04 feet. And this is my air and departures. So those are my airs. Now, what is this telling me? Well, it's telling me that it's not zeros. Okay, that's one thing. So we know that we've got some issues. The larger those numbers are, the worse off you are. Now that's somewhat related to the number of sides. You can expect more air the more sides because you've had more measurements. Okay? But for a 5-sided traverse, you know, of 3,700 feet, that's pretty significant. Okay. Now, if you come up with a really large air in one of these or both of them, the first thing I would do is make sure you didn't flip something here or here, because it could be something just as simple as that. We already know this is good. So it is really easy to just, all I have to do is flip those two guys right there, sum things up, and these are just going to go completely whacked out. Okay. But if you've checked everything, if I check this and I check that I got the distances in the right spot, and that's all good, and I'm still coming up with a large error, you're done. You're sending your crew back out in the field and you're saying, there's something maybe. Okay. All right. Now we have not a great closure, but we do have a bust. Well, let's see what this is actually saying to me. And then we're going to analyze that, and then we're going to go and see how we can determine what we would call our precision. And then we'll look at adjusting this and ultimately get our importance. Okay, so we're getting close to it. So what is this telling? It says I started at A, right? And I ended at A. You see that? That's what this is saying. I started at A and I ended at A. So I started at A. And this is telling me that I am what? South of where I should be. My over half a foot, and I am what? Departure is what? Yeah, it's positive. Okay. So I am south and east of where I should be. So this is saying is if I just ran these in, I'm not ending at A, I'm ending it over here. I'm just going to call this A prime. Okay, so I could be in one of the four quadrants, but this one happened to be with the way the numbers played out from south and east of where I should be. And so the amount of air or the direction in air that I'm out is this way. So this is called your air enclosure. It's usually defined by a capital letter E. Sometimes it's also referred to as the linear misclosure. So more people use the term error enclosure, okay? But you also hear the term linear misclosure, because really what it is, it's a linear vector, okay? It's a vector. It's a distance vector. So E can be determined by simply using these two guys. And we can say that E, or any traverse, is the air and latitude squared plus the air and departures squared. We're going to take the square root of that. So what is that little equation that we're using there? That's the Pythagorean theorem, which is also called the distance equation, because what that's giving you is a distance. Okay. So we're going to just plug those numbers in. And by the way, on your chart, when I do this, I usually drop like down below here, just kind of write it out over here. Okay, so you have this all kind of encapsulated on the sheet. Okay, so you might just want to do that. So my E is going to be air and latitudes. That's 68 hundredths of a foot plus the 1.04. We're going to square those. And we're going to take the square root of the sum of the squares. Okay. Now this number won't be exact either, but if you float it out, you're forcing it to zero. So basically it's saying we're at 1.24 feet. Okay. 1.24 feet. Now, yes,
What did you say that line label B, what is that called?
it's called the air enclosure. And it can also be referred to as linear misclosure. Either one's acceptable to you. I probably use air enclosure more than I say linear misclosure. And E is always going to be positive. Is that true? Yeah, it's always a positive number because why? Because when you square these guys, if they're negative, they come out in the wash, right? Now you can also calculate the bearing angle. In other words, you can determine not only the amount you're out, but you can also determine which direction it's out. I'll show you why that's kind of important. But if we wanted to calculate this angle, does anybody see how we can do that? That would be your bearing.
Inverse tangent
Yes, of what over what?
of opposite over.
Opposite over adjacent?
Yeah.
What's this guy called?
That's
That's your air and latitude. I'm sorry, air and departure over air and latitude, right? So you will be seeing this, that your theta in terms of a bearing angle, because you're never going to get an azimuth, because it's always going to give you an angle between you. Okay, is going to be the arctangent of the air and departures divided by the air and latitudes. So it's always going to be departure over latitude. So let's see what that turns out to be. So we take the arctangent. The departure is what? 104 divided by the latitude, which is 0.68. And that'll give you a decimal degree. So you'll need to, my calculator does, so I have to kick it back over to a degree minutes seconds. Okay, so let's see what comes up with it. Ooh. I get 56 degrees, 49 minutes, and 17 seconds. Is that what you guys are coming up with? Okay. And the bearing is actually what? South. East. So these two things are really happening simultaneously. Now let's look at this. Does it make sense that the direction is 56 degrees and why? Anybody know why that would make sense? It does make sense, actually. Look at the shape of your figure. Which way is it longer, east, west, or north, south? Does it tend to be longer this way or this way?
East west.
So doesn't it make sense that that angle is going to be closer to east-west than it is north-south? Because most of the air is probably occurring in an east-west direction more so than it is a north-south direction. If this thing would be rotated like this, we might experience that more the other way. Now, I'll tell you, that's not always 100% across the board true, but it does tend to be, especially if you have a long skinny traverse in one direction versus the other. You can kind of point to a mistake. So if this was actually like 0 degrees northeast or 2 degrees northeast, that would tell me that I've got more air in a north-south direction. But when I look at this figure, that doesn't really square with what I did out in the field. And that might be why some of these are too long. So maybe I got something wrong in one of my distances.
So if it's a fairly square or like equal both directions, north, south, east, west,
You could probably
it should be closer to 45.
Probably 45, right? But like, again, that doesn't always square that way because it just has how a lot of these things play together. But they will in general kind of tend to do that. So it's a good way of looking at it. Okay, it really is a good way of looking at it. Okay. A lot of people don't even calculate this. This is the more important number because we're going to use this, but we don't use this so often. But if I had a really large bust here, I could use that to maybe determine where I had a mistake. Okay. So this is the number we're going to use. So the next thing we're going to do is calculate which is called traverse precision. And this is the ultimate area for you to determine whether you got a good traverse or a bad traverse and whether I'm going to adjust it. So we're going to look at what we call precision. And this is not the ultimate precision of this. It's what's called relative precision, technically. It's not the real precision. And we've also done some adjustments already. So it's not taking that into account. I mean, it is using it. Okay. So this traverse precision. Precision, usually they define it as P. Now, when you look it up, this is how they define it. Your air enclosure divided by the perimeter of the traverse. So you're just really comparing to the amount of air to the total distance traversed. That's what you're saying. Okay. So if we literally do that, I'll show you what this really is saying. You get a really squirrely small number. So we're going to take 1.24 feet and divide it by the total number of feet we traveled. And when you do that, you're going to get a ridiculously small number typically. If we do that, 1.24 divided by 3.73948. The point is 0.0000 something. That's not really telling you. If you flip this, really just flip it, or take a 1 over x, flip it, you'll get a number that'll come out. So really what I'm doing, I'm actually flipping these, and here's why. what we're saying is this. Is that for every 3,739 feet I travel, I can expect 1.24 feet of air, plus or minus. I'm either going to be long or short. So we like to reference this to 1. So we would like to say, instead of looking at this number, we would like to say, what is that 1 over x? So if you solve for x, what you're really doing is just flipping it. Okay, so really, just take your perimeter and divide it by. Let's see what you come up with. Okay. But if you look in your book, this is the definition of precision. Okay? It's always your area divided by your perimeter. Okay. So what do we do what do we get when we flip that?
2015.
Yeah, so we basically call it 3016. So when we do this, when you solve this, this number comes out to be 3016. And you would express this traverse as a 1 in 3016. This is the precision of your traverse. So for every 3,000 feet we travel, we can expect a plus or minus 1 foot. Okay. So this is horrible. Okay. You probably could use a rope and measure your distances with a rope and probably get better than that. Okay. So there's something really wrong here. Yeah. You know, we already had good, we never had great angles. We didn't have probably good distances. But we got a 1 in 3,000. So for every 3,000 feet we go, we can expect a plus or minus 1 foot close. That's what that's telling me. So what is considered a good precision? I think I mentioned that the other day.
So like 1 out of 50,000 or something?
Yeah, 80, right, 80, 100,000. By today's instrumentations, you should easily be able to get 1 in 80,000, probably higher. Now do keep in mind, that's relative, it's not actual precision. You're probably a little lower based on how you're setting up and that kind of stuff, okay? But still, we need to be higher, okay? If we came up with this in the field, we would completely reject this traverse, send the crew back out and say, dudes, I don't know what you guys did, but you didn't do it right. Got to redo it. But this is our check. This is what we do. Okay? We have to do that. And this is why it's important to understand this process. Okay? So state of Ohio, each state usually has what they call minimum standards, and like for even if you're doing a boundary survey in Ohio, the minimum standard is 1 in 20,000. Now, what that's referring to is the boundary closure. So if you're doing a traverse around that, that has to be at a higher precision, because once you work off of your traverse, anything comes off of that traverse instantaneously drops in precision. So in other words, when I have a traverse out here, and if this traverse right here is a 1 in 80,000 traverse, if I'm locating points off of this traverse, those points are going to drop in precision because they're not part of the original closed loop. Did you get the idea? So that's why we always want to have a high precision on that traverse. And of course, when we're doing construction layouts, same thing. Everything is going to come unglued if you don't. Okay. Does this make sense, guys? All right, so we would reject this. Bottom line is we would reject this. But we're not going to, because I want to show you how to adjust it. Okay. Like I said, if you have a really high precision traverse, when you do an adjustment, you're not going to see much unless you start floating things out 3 and 4 decimal places, 5 decimal places. So the other thing, by the way, too, as I said, if you're doing this in a computer, you know, these numbers are going to be floated out a lot further. That number will be floated out a lot further, and that can sometimes inflate that as well. So you can get higher precisions just because you're using higher precision in your calculations. But keep in mind, you didn't use higher precision out in the field, right? The measurement is what it was. Okay, so you got to be careful with that too. All right, so there's a couple of adjustment schemes that you would use. Some people call this balancing a traverse. Again, I don't like that term balance. You're not balancing anything, you're really adjusting it. And what we're adjusting is we're going to take these guys, and we're gonna tweak each one a little bit so that when we get done, that this is gonna go to 0 and this is gonna go to 0. So you're not balancing anything. You see what I'm saying? You're adjusting it. And what you're doing is mathematically taking this point and pushing it a little bit south and maybe a little west, okay? So you're physically moving it, or mathematically moving it, but it's not moving out in the field, okay? Get the idea? So if we recalculate all this stuff and then take those coordinates out and start using that stuff that's out in the field, things may not agree really well, especially on a traverse like this, with this lower precision. Okay, so the adjustment that you apply is kind of based on what's happening out in the real world. So let me kind of show you when you measure the angles and the distances, there's a couple of things that can happen. So we could say that the angular accuracy, when we measure out there, that the angular accuracy is greater than the linear accuracy. So what I'm saying to you is that we were able to turn angles at a higher degree of accuracy than we were at distances. Okay. So back in the original days of surveying, what did they use to turn angles? Does anybody know? They used way back. They used the compass. Yeah. And they put it on a Jacob staff and they would turn angles with it. It was actually fairly decent depending on how finely it was graduated. But what did they use to measure distances with? A chain, literally a chain, and it was composed of links. So in this case, your angles may have been better than this. So in this case, if we're going to do an adjustment on these guys, where do we want to throw more of the air? Into the angle or the distance? If we're doing this. If this is better than this, don't we want to throw more correction into the distance than we do in the angle, right? So there was an adjustment scheme that was developed to be able to do that. It was called the compass rule adjustment. The compass rule would say, hey, basically, I'm going to assume that your angles are better than your distances, so I'm going to tweak those numbers in such a way that I'm holding the angles pretty fixed, but I'm putting more adjustment in the distance. Okay. So the other premise that you could have is that your angular accuracy was essentially equal to your linear accuracy. So really, this is probably what we operate pretty much on nowadays. Especially since your EDM is built right into the scope of your total station, they're functioning together, they're probably equal. So in this case, we would want to apply a correction such that it's going to adjust the angles basically equal to the distances. We're going to tweak both of them in such a way. So in other words, I'm going to fritz around with both of them. So that's the rule that we're going to use. That's the premise we're going to follow. So the other premise would be that your angular accuracy is less than linear accuracy. And again, you would have ways of tweaking that. So there's about 4 different methodologies of doing adjustments. We have what's called, I already said one, was the compass rule. The transit. Did I say compass rule before? Yes. Yeah, I'm wrong, I'm sorry. The transit rule is the one I wanted to say. The transit rule is the one that would put more error in, or more correction in the angle. The compass rule is a rule that will basically take this premise right there. Okay. It basically says Linear accuracy, angular accuracy are about the same, so I'm gonna adjust things. This is the one I'm gonna show you how to do. This is a good across the board, easy one to do. Okay. This one's a real hard one to do. And then they have what are called Crandall's method. Crandall's method. Might be this one out. And then you have also what we call least squares. So least squares is kind of the more modern adjustment. It takes a lot of high level calculation. You have to have a pretty good software to do that. You're not going to do either of these by hand. Okay. These are allow you to, these are what like most people doing GPS control, they're going to use least squares. A lot of people are using least squares even on doing something like this. It gives them control over everything. And instead of just going in and across the board adjusting everything, you can say, well, this line is really good. I want to hold this line fixed and I want to hold that line fixed. Okay, and I want you to adjust things based on that. That's what least squares allows you to do. I mean, you can do that somewhat with compass rule, but in a computer, you'd have to have more computing power. It would not be accessible by hand. Okay, so I'm going to show you the compass rule adjustment. That's all we're going to consider. Okay, compass rule adjustment. So the compass rule is very simple to do. Basically, it's a two-step process. The first thing we have to do is calculate a correction for each line. Is that going to kick on again? Thanks. Appreciate that. You have to calculate a correction for each line, and then you apply that correction to each latitude and departure. So each latitude gets its own correction, and each departure gets its own correction in this method. Okay. So here is how you do the compass rule adjustment. Let me write this down. It's really simple, not hard to do. It's just you just got to think about what's going on with it. Okay. So what we're going to do is calculate a correction. Your correction for each latitude. Okay. Now it's not just an across the board. Okay. So I'm going to say for line 1, 2, or 2, 3, or 3, 4, whatever. Okay. This is just, you're going to get a correction. You're going to do this for each line. Okay. So it's just a correction. I don't want to just put this because that makes it look like there's only one correction. Okay. You're going to have to do a correction for each line. Does everybody get what I'm saying? Okay. So you're going to take the error in latitudes and divide them by the perimeter of the traverse. Okay. And you're going to multiply that constant times the distance of the line that you want to correct. Okay. So here's what I'm saying. The correction for line 1 to 2 would be this divided by the distance, or times the distance 1 to 2. The correction for line 2 to 3 would be this times the distance 2 to 3. So this is a constant, and then what changes is this. And also, usually you'll see this out here. Does anybody know what that's doing? Putting that negative out there. It's reversing the sign of this. So what that says is this, is if your error and latitudes are negative, all of your corrections will be positive. If your error and latitudes are positive, all your corrections will be negative. Okay, I'm going to show you how you have, it's easy to remember. Okay. So once we get these corrections, then your adjusted latitude is going to be equal to your raw latitude, your original latitude, plus the correction. Okay. So the adjustment, the latitude 1 to 2 would be equal to the original latitude 1 to 2 plus the correction. Notice this is an algebraic addition because both of these will have a sign with them. Okay. So what I'm saying is if this is a positive number and that's a negative number, you're adding a negative number to that. But if they were both negative numbers, you're adding two negative numbers. You see what I'm saying? So this is an algebraic addition. Are you with me on that? Departure works the same way. Correction for departure is equal to your error and departures divided by the perimeter of the traverse. That's a constant for your departures times the distance of the line that you want to correct. And again, we're going to reverse the sign. So we like to put that negative out front. Okay. So we're going to generate a secondary little chart here. And again, you might be able to put this thing underneath on yours. Okay. I'm just going to put it over here. Oh, and I forgot to do one more thing. Let me do this. Also then, the adjusted departure is going to be equal to your original departure plus the correction of that departure for that line. Okay. Two-step process. All right, so watch what we're going to do. This is going to be our correction for latitudes column, correction for departures. We're going to have one for AB, BC, CD, DE, and EA. Okay. Now I'm going to take care of this negative sign right here. Watch how I'm going to take care of this. What is true about our latitudes? They're what, negative? So all of these corrections have to be opposite signs. So I'm just going to come down here and say, these all have to be positive. That's what that negative says. So I don't even have to worry about it. Okay. And what does this say? That my departures are what? Positive. So all of my corrections have to be what? Negative. Because if you think about it, we have to get it down to 0. So in order to trim that back to 0, we got to subtract. And to get those up, we have to add. Okay. All right, so what we're going to do, you can do this in your calculator. Take that 0.68, don't worry about the sign, we already took care of it. 0.68 divided by the perimeter, 37, 39.48, and divide it. If you've got a way to store that number, it's a pretty small number, but if you can store that number, then you don't have to do this a bunch of times. Okay, I know I can store mine, but I got to figure that one out. I'm going to have to do this a bunch of times. So I'm taking this divided by that, and I'm going to multiply that by number by the distance AB. Okay. So I'm going to multiply that times 69.88. Talking too much and not paying attention to what's on the calculator. Okay, let's get a number here for me. Round it to 2 decimal places. 0.13. Yeah. Okay, let's do the next one. Okay, we're going to take the 0.68 divided by the perimeter. Like I said, if you have a storage mechanism on your calculator, then you can just keep that and just recall it. This calculator doesn't store numbers really easily. I got 0.11. Get that? You guys let me know. So we're multiplying that constant times each distance respectively. You should also notice as that as the line gets longer, the correction gets greater. Right? So that also should be true. You guys get any numbers by any chance? That's what I'm looking at. Notice is that the longest line has the most correction, the shortest line has the least. Right? Now, I want you to do something for me. Sum that column up. What'd you get? You gotta get 68. If you don't, you did something wrong. And it should be what? Opposite sign. Now, you don't always get 68. Does anybody know why? Rounding. So what do I do in that case? I'll arbitrarily round one of these so I get it to 68. Okay. I might look at the longest side and put more adjustment in the longest side. It's not that big. If you float that out 3 decimal places or 4 or whatever, it gets better. Okay, you guys see how that works? All right, let's do the corrections for the departures and then we'll apply them. Okay. So we're going to take the 104 divided by the perimeter. And we're going to see that we get more correction here for each line, which should make sense because there's more air in that direction. We got 0.19. So these guys are going to be proportionally larger than the rest of them. I hope you guys have storage mechanisms in the calculator. I know I do, but it's just, I looked it up one time, but it wasn't simple. And let me know if you guys are seeing anything different than what I'm coming up with. 019. There's the biggest one right there. So there's what I came up with. I'm going to sum those up and they should equal to 1. When I do that, so I know I did it right. I know I did it right at that point. All right. Questions? This is the compass rule adjustment. This is the only thing you'll be responsible for. That's not for you. Probably can't even look in a book anymore and find transit rule anymore or surveying. They don't even show you that anymore.
You don't have to adjust it the same way you adjust it.
No. Now, what's going to happen is we're going to apply these corrections to here. And what that's going to do is it's actually going to change your angle and your distance by a certain. Okay. Actually, it's going to be more than it should be because we got such a bad closure. If we had a 1 in 80,000 closure, that number might be 0.01 and that number might be 0.02. So when we did this, we wouldn't see anything unless we carried it out like 3 or 4 decimal places. Does that make sense?
Yeah.
Did I answer your question right? Or
Yeah.
okay. I wasn't sure I was right in what you were saying. So okay. So here's how we apply the correction. We take the latitude plus the correction. Okay, so we're going to take this guy, negative 122.15, plus this guy, which is a positive 1. You have to consider the algebraic sum. Okay, you're not just adding across the board, you're adding it algebraically. So make sure that you consider the sign. So I get a negative. I didn't do that. I just told you to do. So it's gonna be less. Gonna drop a little. So I came up with 122.02. You guys getting that? And I'm gonna take an 11, and I'm gonna add the 11 to that, and that's actually gonna make it just bigger, right? 173.89. So that gives me 174. Okay. Then we got a negative 669.14 plus 0.12. Positive. It gives me a negative 669.02. So those things are gonna increase or decrease depending on what's going on here. So this one we have that 0.18 minus 140 negative. Check my numbers, guys, if you're seeing anything wrong with me. I'm doing this kind of quick, so. We have 14 plus 7, 56, 86. Plus 757.00. Is that looking right? What should happen when we sum this column? Well, let's see. Negative 122.02 plus 74. 669.02 minus 139.96 plus 757. It should go to 0 because we close it. Okay. If it doesn't go to 0, you did something wrong. This tells me it should go to 0. That tells me, because those are the same number, opposite side, that this has to go to 0. So if it doesn't go to 0, it means you're probably adding one of them when you should have subtracted. You went the wrong way, probably with this one. That's what this one is doing. Okay? We're doing all right? So we're going to do the same thing with the departures. We're going to take the correction to departure plus the departure. And again, you're adding them algebraically. Okay, so this one's going to go to negative 680.19. Okay. The next one's going to go to a negative 591.17. Minus 0.19 plus 109.8. So go to a plus 108. 9. We have, let's see, what else? Negative 27 plus 961.10 gives me a positive 960.83. Ultimately, the last one. Again, if you guys see anything mistakes, let me know. Hopefully you guys will see that the cool thing about this, there's all these really cool checks in this whole process. You get to check this point, check this point, check this point. If this doesn't work, something's wrong. This again is going to have to go to 0. So let me see what we get. Once you do this a couple of times, you can really rip through a traverse. So if it seems like it's a lot of work, it is the first time you're going through. But once you do it a couple of times, you'll see it's really not that hard. Okay, not that hard. Okay. You got it? Any questions? Not too bad, right? Not too terrible. All right, so the last thing we're going to take a look at doing is calculating coordinates. Now that we have these guys, we can compute coordinates. The reason coordinates are going to be so important is because it's going to simplify your math when you get out in the field. Everything's usually held in coordinates. And it's just a shorthand way of saying everything. I can give you a list of coordinates, and from those coordinates, you can tell me distances between points, you can tell me bearings between points, you can tell me area between 3 points or more. So coordinates allow you to do all this cool stuff. So what we're gonna do is take these numbers and basically get them into coordinates. So here's how a coordinate would work. You guys are all familiar with Cartesian coordinates, right? You know what I'm talking about, right? No? Or what's another name for Cartesian coordinates? Anybody know another commonly used name? No, that's actually angles. Yeah. Not in terms of Cartesian. It is a coordinate system. Yeah, you're definitely a coordinate system, but that's an angular coordinate system. So a Cartesian is a distance of a distance. Northing and easting. Or the other name I was looking for was rectangular coordinate system. Yeah, but we use the term northern and eastern, right? Okay, so here's what we got. You basically have your grid. And, you know, from a math standpoint, we usually are thinking of this in X and Y. From a surveying standpoint, we're going to think of this as easting and northing. And this is our origin, where we 0, 0. Now, we really never want our site to cross this line or to cross that line. Why? What happens if I cross this line? I'm going to get negative eastings. And if I cross this line, I'm going to get what? Negative northings. And it's not that that's a problem, but if you start doing calculations with negative coordinates and positive coordinates, you can blow it real easily. So what most people like to do is create what's called a false origin. They just push this guy as far southwest as they can, and you work over here so that everything's positive. Okay, you'll never see negative coordinates on any job site typically because they're nasty. Okay, they can give you problems. So here's the idea, is if you have this vector right here, and you know this point A, and you want to determine this point B, so this guy's unknown, and this guy has a value, and usually it's expressed in terms of northing and easting. So get used to that. And that's really saying YX, okay? YX. So if we break this vector down into its components, what's this component called for this vector AB? And this vector? So the first one you said was departure, and that would be correct. That would be the departure A to B, and this would be what? The latitude A to B. So it's pretty easy to see, I think. If you want the northing of B, you're going to take the northing of A, and you're going to add to that the latitude from A to B. Okay. Now, this guy can have a sign associated with it, so you're not always adding latitude. Sometimes you would be what? Subtracting latitude if you're going south. This guy could have a sign too. That's why if you use negative coordinates, you would have to use that as a negative value. But if you don't worry about it, this is always possible. The easting of B is going to be equal to the easting of the point you're coming from plus the departure from A to B. Okay. And we're just going to use that over and over and over and over to go around our traverse. Now the latitudes and the departures that we're going to use here are not these. We want to use these. Okay, everybody with me? So you have a chart here in the back that says traverse closure and area computations, and it really should say coordinate calculations. Okay. So it looks different. It has a line, it has your adjusted latitude, your departure, your point number, your northing, and your easting. Okay. So what I'm going to do is I want you to start. Let me get this set up for you. Okay. I'm going to just erase what I got here. We don't need this. You're going to transfer these guys over into that chart. Okay. Well, let me get the line set up for you. So you have the line here. This is A to B, B to C, C to D, E to E, and E back to A. Okay. So I want you to copy those guys into their respective columns. Put that first and copy these, okay? And then you have one that says point here. I'm going to do mine on two boards. I hope it works. So this will be our northern. This will be our eastern. So I'm lazy. I didn't want to copy it twice. Did everybody get what I'm doing? In that last chart, A, B, B, C, C, D, D, E, E, A, depth. Okay. Okay, how we doing? All right. So what this says is this. We are starting with point A, and we are going from A to B. So you should have A up above, A to B here. And this will be B to C, C to D, D to E, and ultimately E back to A. Does everybody see how I'm doing that in that chart? Your chart, anybody questions on that or not? Okay. Yeah, perfect. That looks good. Good, you guys okay? Zach? All right. So we typically either know a good point or we just make something up random, but remember what we want to do is make sure that we are far enough north and east of our origin so that we don't start out with negatives. If we called this point 0, 0, just about everything in that traverse would have negative coordinates. Okay. Again, that's not a problem technically, but it's going to be a problem when you start dealing with stuff. Okay. So we're going to just go ahead and I'm going to call this point A. We're going to call point A 2000 north, 2000 east. Okay, 2000 north, 2000 east. Now watch how easy this is. You're going to take 2000 plus your latitude, and you're going to write it right here. And then you're going to take this northern plus that latitude, and you're going to write it right there. And you're going to keep doing that until you get down here, and you better come out with what down here? 2000, 2000. If you don't, you did something wrong. Okay. Now we know it has to go to 2000 because our latitudes are 0 and our departures are 0. So I'm going to take this plus a negative. I'm going to take 2000 plus a negative 122.02. And this gives me 1877.88. And then I'm going to take 1877.98 plus 174, 2051.98. Then we're going to take this plus that. It's a negative when I say that plus. Remember, I'm an algebraic addition. Take that plus that. And then ultimately, this should bring me back to 2000. If it doesn't, then I did something wrong. In this case, it's just a math, an addition or subtraction mistake. That checks. There's my coordinates. The point that's furthest south is what in that list? Which point is the furthest south? E. Yeah. Okay. All right, we're gonna do the same thing here. This plus this. That plus that. And that goes back to 2000 as well. So by working these through, I can simply see that point C is the most westerly point. Closest, getting close to the origin, okay? That's getting close. We wouldn't want to go much further than that, okay? All right, that's our process. All right, so we just follow these steps. There's all these nice checks and balances as you get into this. It's a really awesome way of doing things, okay? All right, any questions? You should, in your book, they have there's a chapter that goes over the same thing. I think he basically uses a traverse pretty similar to this. It goes through. So you might want to follow up the reading on that. I've got a homework problem I want you to do. Technically, this won't be due until Wednesday, but you really might want to get started looking at it for Monday. Hold on a second, I'm going to go ahead and stop the recording.